Okay, so we're going to have a look at another question from the topic of ordinary differential equations. This question we are told to solve. It is 2 plus x squared times y double prime plus 5x times y prime plus 4y is equal to 0. And we are told to assume that y equals the sum from n equals 0 up to infinity times an times x to the n is a solution. So essentially the question is telling us to do this using series. So that's what we're going to do. We're going to write down our basic form. Y is the sum from n equals 0 to infinity of an times x to the n. The first derivative, y prime, is therefore the sum from n equals 0 to infinity of n times an times x to the n minus 1. And the second derivative is therefore the sum from n equals 0 up to infinity of n minus 1 times n times a subscript n times x to the n minus 2. I'm going to expand the brackets in this expression. So if I do this over here, this is 2 y double prime plus x squared y double prime plus 5x y prime plus 4y is equal to 0. Now we're going to plug everything in. So we find, under the assumption that this equation has this particular solution form, we get 2 times y double prime, which is the sum from n is 0 up to infinity, times n minus 1 times n times an times x to the n minus 2, plus x squared times the sum from n is 0 up to infinity times n minus 1 times n times an times x to the n minus 2, plus 5x times the sum from n is 0 up to infinity times n times an times x to the n minus 1, plus 4 times the sum from n is 0 up to infinity of an times x to the n is all equal to 0. So now what we're going to do is we're going to rearrange all of these. We're going to put these terms into our series, into our summation forms. So we get the sum from n equals 0 to infinity times 2 times n minus 1 times an times x to the n minus 2 plus the sum from n equals 0 to infinity of n times n minus 1 times an times x to the n minus 2 plus 2, which is x to the n, plus the sum from n equals 0 to infinity of 5n times an times x to the n, plus the sum from n equals 0 up to infinity of 4an times x to the n. This is all equal to 0. Now all of these things have xn as one of their terms. All of these expressions have an xn in them, except for the first one, which has an xn minus 2. So we need to shift this so that x to the n minus 2 is an x to the n. So we have the sum from n equals 0. Now notice when n is 0, the whole thing is 0. When n is 1, the whole thing is 0. So we can actually make this n is 2 to infinity of 2 times n minus 1 times an times x to the n minus 2. We are going to let n equal k plus 2. Because by making n equal to k plus 2, this will make this power k. So this gives us the sum from k plus 2 equals 2 up to infinity of 2 times k plus 2 times k plus 2 minus 1, which is k plus 1, times a to the k plus 1 subscript times x to the k plus 2 subscript down here, times x to the k plus 2 minus 2, which is k power. These 2's will cancel, so this will be k is 0. And now we are going to let k equal n. So this is a slightly strange process, but it does work. So we have n is 0 up to infinity times 2 times k plus 2 times k. Oh, sorry, these all have to become n's. N plus 2 times n plus 1 times a subscript n plus 2 times x to the n. So now we've shifted this power. Now everything in this expression has n powers. And that's what we want. So now we're going to rewrite this whole expression. We find that the sum from n equals 0 up to infinity, 2 times n plus 2 times n plus 1 times a subscript n plus 2 times x to the n, plus our second term, which was the n minus 1 term. So this is the sum from n equals 0 up to infinity of n times n plus 1 times a to the n times x to the n, a subscript n times x to the n, plus our last two terms, which is infinite sum 5n a n x to the n. So 5n a subscript n x to the n, this is from n is 0 to infinity, plus the last term, which is just the 4 term. So this is the sum from n equals 0 up to infinity of 4an times x to the n. This whole sum is equal to 0. Now we can write this all as one big sum, and we can factor x to the n out of it. So this gives us x to the n times the big sum from n is 0 up to infinity of the sum of all of these terms is going to be the sum of 2 times n plus 2 times n plus 1 times a subscript n plus 2 plus n times n plus 1 times a subscript n plus 5n times a subscript n plus 4 times a subscript n. This is all equal to 0. Now, this is either true when x to the n is 0. It's possible that this could be 0 and this would make this true. It's also true when everything in the brackets is equal to 0. And we're going to set everything in the brackets equal to 0. So we're going to say, therefore, this implies that the sum from n equals 0 up to infinity of this whole thing, which is 2 times n plus 2 times n plus 1 times a to the n plus 2 plus n times n plus 1 times a n plus 5n times a n plus 4a n, it's all equal to 0. So now what we're going to start to do is we're going to start subbing in n values, because if this is equal to 0, the sum of terms is all equal to 0, and so we are going to let each term equal to 0. So we are going to say if n is equal to 0, this implies that this first term becomes 2 times 2 times 1, which is 4. So this is 4a2. This goes to 0. This goes to 0. So we get 4a2 plus 4a0 is equal to 0. This implies a0 is equal to a2. And we could write this as a2 is equal to a0. a2 is equal to a0. We know a0 is equal to a0. And we're going to say that a1 is equal to a1. These are just initial setups that we're going to do. And now we have a2 is equal to a0. Now, if n is equal to 1, we find that 2 times 3 times 2, well, that is 2 times 2 is 4 times 3 is 12. We get 12a3 plus 1 times 2, that's 2a to the 1, or 2a subscript 1, plus 5a1, plus 5a1, plus 4a1, plus 4a1 is equal to 0. So this gives us that 12a3 plus 5 plus 4, And we've got to be very careful with our numbers here. If n is 1, this is 2, this is 1. Now, are we missing a number here? No, we're not. So we have 12a3 plus 5 plus 4 is 9, plus 2 is 11, plus 11a1 is equal to 0. And now we could say that this implies that a3 is equal to 11/12 times a1. And we know a1 is equal to itself because we defined it as such up the top. And so now we have a few terms from this particular problem. We can start plugging them into our solution. So therefore, y equals the sum from n equals 0 up to infinity a n x to the n ends up being equal to a0 plus a1 x plus a2 x squared plus a3 x cubed, and so on. But we now have values for some of these terms. So we have a0 is a0, a1 is a1, a2 is a0, a3 is 11/12 times a1. So we get a0 plus a1 times x plus, we said a2 was just a0, so plus a0 times x squared. We said a3 was 11/12 a1, this is times x cubed, and so on. Now we seem to be having two sets, one which contains a0s and x's, and one which contains a1s and x's. So this is equal to a0 times 1 plus x squared plus dot 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 plus a1 times x plus 11/12 x cubed plus dot dot dot, and so on. So therefore, our series solution, y of x, is a0 times some infinite series 1 plus x squared plus dot dot dot. You could find more terms of this if you want. We don't need them here, but you could. a1 plus that, a1 times that plus, sorry, a0 times that term plus a1 times x plus 11/12 x cubed plus dot dot dot, and so on. And so this is the solution form that we're after in this particular question. If, when you look at these particular progressions, you can notice some patterns. So, for example, the first one immediately looks like a particular function, right? When you look at these, sometimes you can tell if something is a function or not. Sometimes you can't, but sometimes you can. We seem to have 1 plus an x squared, and that looks like it may be, for example, a cosine function or something like that. Cosine function is going to be 1 minus x squared, so it won't be that in this case. But if you can recognize that this list of numbers is a particular function, and you can find enough terms to essentially confirm that that is definitely the case, what you can do is you can then assume that that function is indeed a solution. You can plug that function into the differential equation and then solve. We can't do that here because we can't really recognize with any ease what these functions are. But if we did have one that was very clearly defined, and we will see some of these in later examples, where we have a very clearly defined function, then we can turn it in to its shorthand functional form. So if it's cosine or sine or e to the x or log or something like that, then you can test. In this case, we can't test this. So this is where we're going to leave this one.